Hello everyone, my name's Dr. Vile and welcome to my A-Level Chemistry YouTube channel. This channel is all about getting you ready for your A-Level Chemistry exams, and this video is going to focus on pH titrations. So we're going to be looking at how you can do a titration but without using indicator, but instead using a pH meter. Now it would be a good idea before you come to this video if you're already familiar with how to do a regular titration and titration calculations, although we will recap it as we go through. If you find the video helpful, remember to like, subscribe, share, and keep checking back for more content. So the first example we're going to look at is the reaction between HCl and NaOH. Now hydrochloric acid is an example of a strong acid. That means it fully dissociates into H+ ions and chloride ions in solution. So a strong acid fully dissociates into the corresponding ions, and sodium hydroxide is a strong base, and that means it fully dissociates in solution as well. So in solution, sodium hydroxide exists as Na+ and OH-. And what's going to happen, I'm jumping around here a little bit, but the H+ ions and the OH- ions are going to stick together to form water. And then the chloride ions and the sodium ions are going to form sodium chloride. So in terms of completing our balanced equation, the HCl combines with the sodium hydroxide to form sodium chloride, NaCl, and water, H2O. So it's a neutralization reaction. You're taking an acid and an alkali, combining them together to form a salt and water. Now HCl is acidic and will have a pH of less than 7. And sodium hydroxide is an alkali and will have a pH greater than 7. And when we hit the point of neutralization, you'll have exactly sodium chloride and water. And if we can get to exactly that point where there's only sodium chloride and water in the mixture, the pH will be bang on 7. And normally you'd use a chemical indicator, something like phenolphthalein, which will change colour from pink to colourless or colourless to pink, depending on which way around you do it. But what we're going to look at is how you do it without a indicator. So we're going to use a pH meter. Now in simple terms, a pH meter is a probe that you put into solution and it'll give you a pH reading on the screen. We need to understand what pH actually means. pH is a measure of how many hydrogen ions are in solution. So pH is calculated using the formula minus log times the concentration of H+. And because it's a log scale, when the concentration of H+ ions is high, the pH would be low. And when the concentration of H+ ions is low, the pH will be high. So how you do this practically is you take a beaker containing, say, let's say your acid, and you put your pH meter in it and you'll get a reading. And then you have a burette and you add some sodium hydroxide, perhaps 1 ml at a time, give it a good swirl and record your new pH. And you repeat that, and what you'll end up with is a graph of pH on the y-axis and then volume of NaOH added in milliliters on the x-axis. And what you'd expect to happen is a bit strange actually. The pH will stay relatively low to start with. Remember, this is hydrochloric acid, and then suddenly it'll leap up and then it'll flatten again. It doesn't go up kind of gradually like this. That doesn't happen. It goes up, well, it flattens and then it suddenly shoots up and then it levels off. And if you were doing a titration calculation with this, what you'd do is you'd read off the middle of your vertical region, which is the middle of your steep section. You could read it down then to read off the volume of NaOH required, and then you could use it in your titration calculation. But I guess my question is, why does this graph have this distinct shape? So here's a much neater version of what we were talking about. You've got the strong acid versus the strong base. and you have that very, very steep section. Well, think about it this way. At the beginning, you have an excess of hydrochloric acid in there, and the hydrochloric acid contains H plus ions. Remember, it's a strong acid, it fully dissociates into H plus ions. And then you add OH minus, and you get water. But at first, in this section here, there is an excess of the H plus ions. So when you add OH minus ions to it, you form the water, but there's still loads of H plus ions left in solution. And then you get to the vertical region, and at this point, the amount of H plus equals the amount of OH minus, so you end up with pure water, which is neutral pH 7. However, once you get past this point into this section of the graph here, you end up with an excess of the OH minus ions, which makes the pH particularly high. So at the first part of the graph, you have an excess of H plus ions, which means the pH is low, and then at the end you have an excess of OH minus ions. And as I say, to do your titration calculation, you read off from the middle of the vertical region and read down to work out the volume required for neutralization. Then you can just treat it as if it was an ordinary titration in terms of doing calculations. Things become a tiny bit more complicated when we use a weak acid, such as ethanoic acid. I need to explain what I mean by a weak acid first. A weak acid is one that only partially dissociates into its ions. So ethanoic acid is in equilibrium with H plus and the ethanoate ion, CH3COO minus. And because ethanoic acid is a weak acid, this is reversible. An equilibrium is established. And therefore, we can write out an equilibrium constant for it. We'd say that Ka is equal to the concentration of the H plus times the concentration of the ethanoate ion divided by the concentration of the acid, CH3COOH. So Ka is a measure of how far this dissociation occurs. So if Ka is big, this equilibrium lies to the right hand side, and if Ka is small, the equilibrium lies to the left hand side. And what we notice here, to start off with, firstly, the original pH is a little bit higher because we are dealing with a weak acid. And then the graph has like this little kink here, then it flattens, and then you get your steep section. So a couple of points. Notice the steep section here is pretty much entirely in the alkaline region. That's the first thing to notice. The steep section is primarily in the vertical region. And then, secondly, we need to notice this little kink here, and there's a sign here that says at half the neutralization, pH equals pKa. And that might just seem a bit random. The neutralization is 25 centimeters cubed. So half the neutralization is 12.5 centimeters cubed. And at that point, you can read off the pH, which would be something like 3.8. And we'd say the pH is 3.8, and therefore pKa is 3.8. I'm going to explain what we mean by pKa in a second. But where does this come from? This pH at half the neutralization equals pKa. Well, let me just clear some room a second, and I'll try and talk you through it as best I can. To understand this, you need to be kind of fairly clued up on how buffers work. So to make a buffer solution, you take a weak acid, like ethanoic acid, you react it with sodium hydroxide, NaOH, and what you form is the salt, CH3COONA, and water. Now, the way that you make a buffer normally is that you'd have excess of the weak acid reacting with the sodium hydroxide. So basically then all of the sodium hydroxide gets used up, and your buffer is composed of ethanoic acid and the salt. And then the formula that we use for this is that the concentration of H+, in other words your pH of the buffer, is equal to Ka times the concentration of the acid over the salt. So to work out the pH of your buffer, you need to know the concentration of the acid and the salt. But going back to this point here that we talked about, let me just clear off some of this a second to try and explain. At half the neutralization point, half of the ethanoic acid has been used up, which means we formed an equal amount of the salt because it forms in a 1-to-1 basis. So half of the ethanoic acid has been used up and the same amount of the salt has been made. So what that means is the concentration of the acid and the salt are the same. So if they're the same, these numbers here just cancel down. And what you're saying then is the concentration of H+ equals Ka. Well, pH is minus log of H+, so we can say that pH is equal to pKa. And the reason is that pKa is simply minus log of Ka. So when you get to this half equivalence point, the concentration of the acid and the salt is the same. Therefore they cancel out, and therefore H+ equals Ka or pH equals pKa. So if you have a weak acid versus strong base graph like this, you can read to half the equivalence point, read off the pH, which in our case is 3.8, which means pKa is 3.8, and therefore we can do a calculation and we can say that Ka is 1.58 times 10 to the minus 4. So by using this we can calculate Ka and then do other calculations with it. So I hope that's helpful for a weak acid, strong base. It's a very popular question where they'll give you a graph like this and they'll ask you to calculate the Ka or some calculation linking to that, and you just read off to half the equivalence point. And just to close, I just want to talk about then how we'd use these graphs to work out which indicators we would use for a neutralization reaction. It's worth noting what an indicator actually is. An indicator is a chemical compound that changes its structure depending on the pH. And as its structure changes, its colour changes. So phenolphthalein, for instance, really popular one, has two different colours, colourless or red or pink as you would see it. And in acid it's clear, colourless, and in alkali it's pink or red. And what we're doing is finding the pH range where this colour change takes place. So phenolphthalein changes between about 8 and 10, which is about here on your graph and about here on your graph. So it falls perfectly within the vertical region. And what you have to do is pick an indicator that changes colour in the vertical region of your graph. So if we look at the strong acid, strong base, the vertical region is pretty much from here, which is 11, to here, which is about 3. So we need indicators that change between 3 and 11, and that is basically all of them. So for a strong acid, strong base titration, you could use any of the indicators that you wanted to. However, things are a little bit different for the weak acid, strong base scenario. If we look here, the vertical region goes to about 10, 11, something like that, and it doesn't start till about 6, which basically means that these first 3 indicators here, methyl orange, bromophenol blue and methyl red, would not work because they change colour in the acid region. So we can't use these, but we could use the bottom 3 because they change colour in the vertical region of the graph. So one of the questions would be, they give you a table of data with these indicators, and you have to pick a suitable indicator for your graph and explain why it would be suitable. Well, it changes color in the vertical region, or the point of equivalence on your pH titration graph. Anyway, thank you for taking the time to watch this video. I hope it was helpful. If it was, remember to like, subscribe, share, and keep checking back for more content. Thanks everyone.